So for these kind of problems, you'll need to be able to do a quick sketch like this for whatever function I give you. Logarithms, trigonometric, exponential, polynomial, obviously. So you graph it, you get some ideas. So some of you guys might be doing this one, some of you guys might be doing this one. I'll go ahead and do both, and I'll show you how finding both is stupid quick using what we do in the calculator. So I'm going to call this xn for x negative. Well, that might not be a good idea. That's xp, and this is x np. It's not positive. So I'm going to find xp first. I'm going to find the x positive one first. So it looks like, get out of there. Why am I circling those? Bam. Bam. What are these things mean? So what's a good guess for x positive? Anybody do this one? What do you guys use as a guess for this root? 0.5? Okay, cool. So let's say x1 is 0.5. Real quick, what do I need here, obviously? For the method, I've got to get what f prime is. F prime is going to be 2x. This goes away. What's the derivative of this? What's the derivative of that piece? Yeah, 2 to the x ln 2. A little adjustment since the base is not e. So then to set this up, I'm going to want x2 is going to be 0.5, so I'm going to say answer minus f answer divided by f prime answer. That's the main idea behind this. So now let me be a little more precise for myself. x2 is going to be answer minus answer squared minus 2 plus 2 to the answer divided by twice answer plus 2 to the answer natural log of 2. Whew. So I'm merging the theory behind the idea with the practical application in the calculator, how to use it. So now, let's see what happens. So I want my guess, and somebody else could have used something a little different than 0.5. So if I want my guess to be 0.5, then I can build in this idea, answer minus all this business. Divided by twice the answer plus 2 to the answer times natural log of 2. So here's x2, x3, x4. I didn't really tell you how this should converge pretty quickly. Yeah, see, it's already starting to, there you go. Is everybody cool with that? You guys, anybody do that one? Did you get that? This process can actually handle slight mistakes to the derivative. Don't be lax because of that, because you don't know what slight means in this context, but it'll just take longer for it to get there with certain very small mistakes to your derivative. What if I would have, now watch, this is too beautiful. Did anybody else use a different first guess? Anybody? Yes? 1.5. 1.5.
Got the same answer.
Yeah, these are really nice functions. So you can, how close do you have to be? Not all that close. So let's see, if I got 1.5, and then I could just go second enter, and do the whole thing again. In the middle of doing this process, you can change your initial guess. You just type it in, and then hit second enter, and you got all that stuff sitting there waiting for you. Enter, 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 and it gets there pretty quickly. Cool. Let's try something crazy. Let's try 10. What if I have a first guess of 10? That's nowhere near right. There we go. Look, see? Why does that still work? Because these functions are so nice. It's a freaking exponential. I mean, you can't get much better as an exponential. It's almost its own derivative. And then you got a parabola. Okay, you can't. I mean, come on. So those are beautifully nice functions. It can handle being kind of far away. Yes? So, like that. I like it. Yes. Or, give me a list of x1, x2, x3, x4, x5. And on the test, I would say correct to within 4 or 5 decimal places. Because some of the ones we're going to do, they would take like 20 iterations to have the whole calculator screen agree. So I'm going to say, I'm not going to make the whole screen agree. I'm just going to say the first 4. So maybe you'll stop at the 9th time instead of the 20th time. If I try 0, 0 is interesting because it's kind of like in the middle of those two. So there's 2 roots. If I get too far away from one root, the process might actually pick up the other root. You guys see? So let's see what happens if I try 0. Ah, there you go. It went back over and caught that one. Cool. So anybody do the other one? What looks to be a good guess for this guy? A little bit less than, according to Mike Crappy sketch. The other answer looks to be a little bit less than -1. No, yes? So where does this guy meet this guy? Looks to be a little less than -1. So maybe I can try -1.1, and then just start the whole thing going again. Bam, 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 bam. There it is. Cool. They can check this, of course, and I want you to really think about this fact. When you check this using that 0 function, you're just asking the calculator to do what we just did. The algorithm will actually have a few modifications to take care of some of the major places, the flaws, but it is built off of this idea, period. I like it. Let's try to go crazy back here. Let's go -200. Look at that shit. Yeah. It's going to get there. There we go. See, the little dude got there. Again, why? Because here's the really big reason why. If we can figure out when this is equal to 0, what would be, no, really watch it. If I can figure out where f prime is 0, anything near there, why would they freak this thing out? Possible. Yeah, and in the process, it would have a 0 on the bottom. So obviously, if I used exactly the x that makes it 0, that would be a problem. So if we knew where this thing equaled 0, if I tried to plug something in near that, it would probably kind of at least take it a lot longer, if not freak out entirely. Maybe. But again, why is this able to handle negative, what did I put in there, 200? And that's really far away because these are nice. Didn't have any freaky slope points or anything, except for that one place maybe. Okay.